Okay, so today we're very fortunate to have our own Owen Lynch giving a talk about, I think, some of his current and future work. So this will be Owen's farewell talk at Topos US. He's headed off to do his PhD at Oxford and to work on the ARIA program in the UK. So we're sad to see him leave, but he's going to keep doing excellent things, and we're all very excited to see how that develops. So thanks, Owen. Take it away. Yeah.
Thanks, Evan. So this is my last talk, and I wanted to do three things with this talk. One, have fun for myself. Two, talk about some new category theory. And three, give context for that new category theory. Unfortunately, all of these goals are mutually contradictory, so this is going to be a bit of a mess. But with that, let's get started. So I'm going to start by saying, like, this talk is about systems. What do we talk about when we talk about systems? What are systems? What does that mean? And my perspective on this, because this is my last talk at Topos Berkeley, I'd like to actually thank the people who have shaped, the people who I've been in contact with through Topos, who have shaped my understanding of this over the last really 4 years. So I'd like to say thank you to David Spivak, David Jazz, Evan Patterson, James Fairbanks, Brendan Fong, Sophie Libkind, John Baez, and also Matteo Capucci for really, like, I think if any of these people did not teach me things, this talk would be different. So thanks for that. So what do we talk about when we talk about systems? So this talk is going to be about a particular philosophy of what is a system. Namely, it's going to be about what I'm going to call a directed system. But in order to say what a directed system is, I'd like to contrast it with what an undirected system is. So basically, an undirected system is basically just a collection of variables and then equations between them. And this is sort of how physicists think. So laws, when you have a law, it doesn't tell you how to compute one variable in terms of the other. It doesn't say that, like, one variable causally precedes the other. It just says, like, this equation holds. Now, you might use it to compute, but it's not inherently directed. And so if you take this notion seriously and try to develop theory around it, what you get is something like a system is a radical differential ideal in a free finitely generated differential ring. What the hell does that mean? Well, basically, it means that we can use, it's like we have a bunch of variables, and then we set equations that use, like, algebra, constants, and derivatives. So something might look like this, where the derivative of momentum is negative kx, the derivative of x is v, and then we also have this algebraic constraint, v equals p over m. So this describes a string. A spring. And undirected systems, we compose these by, oh, well, actually, I already drew this. We compose these by, you draw like a big bubble, and you have bubbles inside, and you put, like, variables and laws in each of the bubbles, and then you say, okay, this variable in this system is equal to this variable in this system. So you just compose undirected by setting their variables equal. And notice that this is also a pretty undirected notion of composition. We're not saying one system feeds into another system, or we're just sort of constraining two systems to give the first, to set the two variables equal. Now, to contrast, we have Moore machines. So Moore machines are a directed notion of system composition, which means that there's really a notion of cause and effect. The simplest notion of a Moore machine is just a function with an update, a set with an update function on it. And this describes, you might write this down as an equation as Sn plus 1 is u s n. And I'm writing this special equation to say that this is really a computation. I have some state at time n, and I want to get the state at time n plus 1. And this is a closed Moore machine, also known as a discrete dynamical system. Slightly better, if we want to, is to allow this to take some sort of input. So what that looks like is now u goes from s times b to s. So we allow how the state changes in time to depend on some input. So now the equation is Sn plus 1 equals u Sn and then Bn, where Bn is some other sequence that's given externally. And so this allows us to give an input to our Moore machines. How do we give an output? Well, we also would give a function from S to A. So with this, I can take a sequence of B's, start in some initial state, and get, if I say A n equals f of Sn, this allows me to sort of input the B's and output a bunch of A's. So it turns a stream of B's into a stream of A's, and this is all like computational. It's not relational. Okay. But one thing to note here is that this A can only depend on the Sn. It can't depend on the Bn. What happens if we want to allow the An to depend on the Bn? Well, then we get a notion of called a Mealy machine, which basically looks like S times B. The update function now takes in an S and a B and outputs an S and an A. And this seems like a little bit innocuous, like, okay, why not let the output depend on the input? That seems pretty logical. But it means that the evaluation order is different. When you're composing Moore machines, you can say, okay, every Moore machine output your output, and then use that output to compute the next input. And this is actually what you see here. Where the output of this Moore machine becomes the input of this Moore machine. You can't do that with Mealy machines, because in order to evaluate this output, you need to first give it this input. And in order to evaluate this output, you'd first need to evaluate this input. So the additional flexibility that we gave actually constrains the way that we can compose them in a problematic way.
Quick question.
Yeah.
Where did S0 come from?
The universe. No, I don't know. You get to choose. So now this is in discrete time. What happens if we want to do this in continuous time? Well, we just, right here we had Sn plus 1 equals u of Sn. We just replace that with like S dot equals V of S. And now, so this looks a lot like these variables with equations, but this is actually slightly different. The data of the Moore machine is really this V function, not a relation, that tells you how to get the vector field into, like that actually gives you a vector field, not just like a relation on the derivative. And you can make similar modifications, so you can say like, in order to have input, you could have like S dot VSB. And now this sort of turns a continuous stream of B's into a continuous stream of A's if you also have A equals F of S. And we could sort of add like T parameters to all of these to make that clear. Okay, great. I'm on time for lens speedrun. So lenses are how we make sense in a categorical way of the composition and also the definition of Moore machines. So what is a lens? Well, it's a lens is a morphism in a category of lenses. It's one of those things. But really, like, okay, what is a category of lenses? It's something that results from a certain construction. And well, there are actually several lens constructions. So really, a lens is kind of a vibe. But I'm going to give some examples of lenses, and then I'm going to give an example of a lens construction. That is sort of the main lens construction that we care about. So simple lenses. So before we can talk about lenses, each type of lens comes with its own type of arena. So for simple lenses, arena equals pair of sets. And the notation that for arenas that we're always going to use is this. And in this notation, this is the base and this is the fiber. But what exactly that means will depend on the type of lens that we're using. So for simple lenses, this is just two sets with no relation between them. And then we draw a lens like this. And for simple lenses, what does this mean? Well, it means that we have a function a to b, and then we also have a function a times b bar f sharp to a bar. And so we can go from a to b, and then if we have an a and we have a b bar, we can get back to a bar. How do we compose these? Yeah, these are morphisms in a category. How do they compose? Well, we give the bottom map by just going like boop, boop. And then if we have an A and a C bar, then we can use this B. We can use the B that we get back a B bar. And then we can use this to get back an A bar. So these are kind of like, basically they have a forward pass and then they have kind of like a feedback. Now we're going to talk about slightly more advanced lenses. So we're going to talk about the fibered version of dependent lenses. Actually, no, we're going to talk about the indexed version of dependent lenses. So in the indexed version of dependent lenses, an arena, we're going to change the meaning of this. This is going to be A is a set, and then A bar is a function from A to set. So now like A bar depends on A. And a lens, A bar, what this means now is we have F sharp, and this F is the same, it's just a function from A to B. F sharp now has A in A times B bar of F of A to A bar of A. So if I have an A here and something living on top of, like an element that depends on F of A, then I can pull it back to get an element that depends on my original A. So now there's a general construction that can give me both simple lenses and dependent lenses and all sorts of other lenses, and it's called Grothendieck lenses, also known as functor lenses, or if you want to annoy David, Spivak lenses. The ingredients are we have a category C of base objects, and then we have a functor bun C op to cat. And the idea here is that bun of A in C is going to give me the category of allowable A bars for A. So in the case of here, it would this would just be like sets. Here, this would be sets that depend on A. And then now the meaning of A bar is like A is in C, and A bar is in bun A. And the meaning of a lens like this, B bar, is that F goes from A to B. This is a morphism in C. And then F sharp goes from F upper star B, where F upper star, remember bun is a contravariant functor into cat. So given a bundle over B, I can pull it back to a bundle over A. And so this type checks as this F sharp is a morphism in bun A. And these all compose in basically the same way as here, where I compose the bottom maps and then I compose the top maps going in the opposite direction. Oh dear. Okay. Then, so this gives me a general recipe for lenses, but how do I get generalized Moore machines? Well, whenever I have this setup, I can talk about a notion of tangent bundle. And the idea is that T A in C is a bundle over A. So for every object, I have a special bundle over it, which is somehow going to be about updates. So in the simple case, we have T A equals A. And really, you should think about this as like A. In the dependent case, it's like this. And let's look at what this means. So if I now have A times A, sorry, this should be. I'm going to say A bar of A in A equals A. So yeah, this is a dependent family over A. And so now if I have F sharp goes from A in A times B bar of F, F of A to, well, now it's just going to be A again. This is going to say if I have a state here and I get an input here, then I get a new state. So Moore machines are lenses of this form, where this left-hand side is constrained to have the tangent bundle. And in the discrete case, that means I have this update function, which gives me the next state. In the continuous case, this tangent bundle is actually a tangent bundle. So basically what this says is, given an A and a B bar, I get like a tangent vector to A, and that's going to give me like a parameterized ODE, again of the form like S dot equals V S B. So this V is now the F sharp. So I won't get into that too much, but yeah, the point is that once you move to this generalized Grothendieck functor / Spivak lens perspective, and you give a notion of tangent bundle, then you get a notion of Moore machine that is specific to the setup that you gave, and that generalizes different types of Moore machines. Yes?
When did capital A and C start? How can we have elements of that if it's just an object of the category?
So in this case, I'm working with C equal to set.
Okay.
And yeah.
Anytime this makes sense, or that's not generalized?
Yeah. That's not. This is just the definition for C equals set, and then like bun is this. Yeah. Yeah. What's up?
Do these tangent bundles satisfy some universal property, or is it extra like data you have to?
It's a good question. No, in general, it is extra data. They don't satisfy universal property. They probably do have to satisfy some properties, though. For instance, you might want it, if like C is Cartesian, you might want it to interact nicely with a Cartesian structure. Okay. So, let's speedrun. So, I am running 7 minutes late. Okay, great. DCST philosophy. So, this gives me like a very general notion of system, namely for, and this is what David Jazz calls a doctrine, for any like base category and bundle category. I have a notion of Moore machine. How do I want to organize these? Well, in the philosophy of category theory is that you should study objects not by studying sort of their intrinsic definition, but by studying how they relate to other objects. So we should study systems by how they relate to other systems. So that means we need some way of comparing systems. But ACT philosophy, applied category theory philosophy, is that big systems should be built up of little systems. So we also need some way of composing systems. And these sort of two dimensions of comparison and composition lead us to double category theory. So DCST stands for double categorical systems theory. And in the undirected case, when we're just working with like these big bags of variables and equations, well, actually we can kind of get away without doing double category theory because the morphisms between systems are rich enough that universal properties in the category of systems and morphisms between them allow you to glue systems together. Actually in this diagram, this composition was achieved by a limit. And in general, when we move to directed systems, we still should be using universal properties. So we should have, we should be able to use limits, but we're not gluing systems together in the same way. So we really only probably will have products, not general limits or pullbacks. But we should retain some amount of composition just from universal properties of the category of systems and morphisms. But there's also sort of another aspect of composition, which is that like directed systems are built out of functions that calculate things. So in the case of like just a Moore machine, you actually calculate the next step and you calculate the output. There should be some composition that actually uses those computations and composes those computations. And in general, that's not going to be given by universal properties in comparison. So once we're moving to directed systems, we actually need a primitive notion of composition that is not just determined by the comparison morphisms. And as a side note, both comparison and composition use functions. and these sort of have a different character. The functions in comparison sort of can exist platonically. They're not involved in actually running the system. Like if you try to implement a Moore machine, you don't have to implement in the same as like machine code that runs when the system is running the comparison morphisms. But the functions involved in like the actual updates, those need to be computable in some sense. So that's another reason why we want both of these, because even though these might both involve functions, they're sort of a different notion of function. Okay, so how does this all cash out in practice? So I've drawn this nice diagram where the idea is that we're composing these. These are systems, we're composing these, and then we're also relating systems, and we're relating the composition of this to the composition of this. So that would be a nice story if that's how double categorical systems theory worked in practice. But sort of the paradigm of double categorical systems theory that is in the David Jazz book, which really introduced double categorical systems theory, is not really this. Because there's actually a lot more stuff. We make a distinction between system. A system has an interface, but a system is not a morphism like this. And then we have composition diagram, which is a morphism like this. And so we in order to fully specify a double categorical systems theory, we need a double category of interface comparison, composition diagram comparison. And then on top of that, we need like this lax functor to span, which is also lax symmetric monoidal, which gives us system and systems comparison. It's a lot of data. And also, we're using symmetric monoidal double categories and for all of this, which means that in addition to having all of this data that we need to specify, we also need to check coherence for weakly symmetric monoidal double categories, which is an absolute nightmare. So we should have listened to Levere. Levere said symmetric monoidal categories were a mistake. And really, as much as possible, things should be given by universal properties. So like I said, here, composition can't be given by universal properties because we're not gluing systems together. It's not limits. We're actually composing the underlying morphisms, in the underlying functions that compute things in those systems. But a certain type of composition, namely parallel composition, independent composition, should be given by product. So I propose, instead of having a double categorical systems theory like being all of this data and monoidal categories, a double categorical systems theory should just be a Cartesian double category. Okay, I made up some time. 11:30, part 5, great. Now we're going to get to the actual point of this talk, which is to talk about a Cartesian double category of system templates. So in Jazz style double categorical systems theory, we had this distinction between a system and a composition diagram. But we want to reduce these 6 things to just 4 things, because there are only 4 things involved in a Cartesian double category. So we're going to have to actually blend system and composition diagram. And what I'm going to call the blending of a system and a composition diagram is a system template. And the idea of a system template is that it's something that you can plug a system into, or it's something that you can plug another system template into to get a system. So it's like a system with holes in it. So unlike typically composition diagrams, they don't have any state. A system template can still have associated state in it. And this is actually, in retrospect, this is a very natural thing. Because when, imagine if you're creating a graphical editor for string diagrams and you want to use, or so for wiring diagrams, and you want to use these wiring diagrams to talk about systems, and a wiring diagram has more than 2 boxes. Well, in the process of filling those boxes, there's going to be a point where some of the boxes are filled and some of the boxes are not filled. And in traditional double categorical systems theory, we don't actually have a way to talk about that intermediate state when some of the boxes are filled and some of the boxes are not filled. So the idea of, moving to here, we say that actually the primitive thing should be this partially filled wiring diagram. And in the case that it's fully filled, then that's an open system, because it still has output. In the case when it's not filled at all, then it's sort of like a stateless system template. Yeah.
So are we saying that we're trying to basically blend like the 2 viewpoints on like string diagrams / wiring diagrams, where a string diagram is typically like a particular morphism in a monoidal category, whereas a wiring diagram is a morphism, and an operator it's a pattern of composition. And what you're saying is that there should be a single concept that subsumes both of those.
Exactly. Yeah. And moreover, that should be the horizontal morphisms or loose morphisms in your double category, in your Cartesian double category.
So what's different about this this system template that's partially filled from, there's another system template where I like forgot where I started and just have this partially filled thing with just the one hole, right? So you're saying you need to track where I started from rather than just filling a hole and now I have a new system template, fill another hole, I have a new system template, eventually it becomes closed, it becomes just an open system.
Yeah.
So you're tracking the state.
Yeah, I'm saying that like the intermediate products along the way of filling up a wiring diagram should be mathematical objects that we treat on an equal footing as like the totally unfilled wiring diagram and the totally filled wiring diagram. No, they're not other wiring. Like in the typical way that people do wiring diagrams don't have like an associated state space.
I mean, it just seems like if I plug one wiring diagram, that might not be.
It's not that I'm plugging a wiring diagram in here. I'm plugging an entire Moore machine in here.
So in the operatic viewpoint, the thing that is shaded there would be something of the algebra.
Yeah.
And it wouldn't exist in the operator itself.
Yeah.
Yes, that makes sense.
And sort of the interesting thing though is that you can take a traditional DCST theory and sort of build one of these in the same way that you can take an operad and an algebra over that operad and build a new operad. But if you start from this perspective, there are some systems that you can't build just via that. And that's sort of what I'm going to get to. But this is sort of an important special case. So what is this? Well, basically, one way of thinking about this is that if my system template originally was something, oh, this is not a good marker. Nice. Oh, much better. If my wiring diagram was originally something like this, namely it had like an A bar, a box where you expected to put a Moore machine that outputs A's and inputs A bars, and another Moore machine that outputs B's and inputs B bars, and then creates a Moore machine that outputs C's and inputs C bars. Now, if I partially apply this, if I put in a Moore machine on the B, then what do I get? Well, I get A bar A S T S C bar. So this has a interface, and then it has this state parameter. Now this state parameter doesn't just have an arbitrary bundle. It has the tangent bundle. So when I get a feedback here, that feedback is just going to like pass through the A bar, but it's actually going to tell my state how to update. And how do I compose these? Well, and so now I think of this as a morphism from A bar A to C bar C. And in the special case that like A bar A equals 1, 1, then this is just a Moore machine on C bar C. But now we also have another interesting special case where C bar C is 1, 1. Now what is this? Well, it says given A and S, well the bottom map does nothing because it just gets sent to 1. And then the update now gives me a update in S and a event here. Well, what is that? That's actually a Mealy machine. Remember a Mealy machine, like given the input, I now get the output. So this actually shows that like Moore machines and Mealy machines aren't necessarily incompatible with each other. It's just that they have their input and output are different. The output of a Moore machine is here and its input is here, whereas the input of a Mealy machine is here and its output is here. And that actually clarifies something, which is that type theoretically, the input of a Moore machine can depend on its output. And similarly, the output of a Mealy machine can depend on its input. So yeah, in my ACT talk, I called these like Moore Mealy machines, but they're also just parametrized lenses. And this notion of parametrized lenses comes from Matteo Capucci. And basically what happens here, how do I compose these? Well, if I have like, I'm just going to say A, S to B, and then I have B, let's say X, Y to C, well, I'm going to end up with something A times X times Y to C. So the idea is that the state space of this composed thing is going to be just the Cartesian product of the state spaces of each of them. So and this pattern generalizes in the specific instances of dependent lenses and continuous dependent lenses. For dependent lenses, the bicategory where the morphisms are of this form is called org. And in the continuous case, in our paper, we called it corg, continuous org. But it's a general pattern that you can build whenever you have the starting setup of a base category and a bundles. But as of the compositional physics paper that we wrote in the spring, we didn't have a good notion of how to turn this into a double category. We had this as a bicategory. We had various contenders for what the vertical morphism should be if the horizontal morphisms are given by this. But none of them were quite right. And in order to and so the process of figuring out how to tweak this in order to make good vertical morphisms was what led to stateful lenses. So what is a stateful lens? Well, it's kind of a lot of data. We're gonna give it in the fibered case. We'll give it in the indexed case. So basically, a stateful lens from like A bar A to B bar, and I'm going to draw this as like, it's like a lens, but then it has some state that can update in the middle. This consists of a family A to set, a readout function R from S A to B, and then a feedback function, which has A, S, A times S in SA times B bar of RAS to A bar of A. And what does this say? Well, this says that if I have a element of A, I have a state that's compatible with that element of A, and then I have an input at the readout at that state, then I can get an element of A bar. I can feedback. So now it's like a lens, but the feedback part is also depends on sort of the state of the lens. And then finally, I have an update. So update is also a little bit long. I'm just going to, it takes all of this data and then also a new A bar in A and produces a new state. So the way that a stateful lens works is you can think of it like a box like this. It has some state. It outputs something here. And then someone else gives it an input on that output. It then outputs something here. And then someone else gives it a new input here, and then it updates this state. So sort of the flow of data through a stateful, like that, and that's like one full cycle of the stateful lens. I output, I get an input. And I think of this as like, I output state, I get an input event, I output an event, and then I get a new input state, and I update my current state to be compatible with that new input state. Composition of stateful lenses essentially works like this, except because now my state can be dependent on my parameter, there's an additional complication. So, well, notice it's actually probably easiest to say if I slightly reframe this as S. If I take a Grothendieck construction and make the dependency of S on A like this, and let's maybe say that this is X. So X is equal to like A in A, S A. This is Y. C. So now when I compose these, I actually pull back their state spaces. So a state of the composed stateful lens is given by a state of the first stateful lens and a state of the second stateful lens that are compatible on the intervening base. And then like, how does the feedback and update work? Well, it's pretty self-explanatory. Like, I get a new readout here, I get a feedback here, I pass that along here, I get a feedback here, then I get an update here. That allows me to update this, and then I finally update this. So it all sort of just computes. So the interesting thing for me about stateful lenses is that there is this pullback component, which is very similar to way back at the beginning when I was talking about these undirected systems, because undirected systems compose by limits. And we have a limit here. but it's sort of a very controlled limit in that, like, as long as I'm happy with this, and I don't really have to solve many equations for this if I do this in the dependent type verse for reasons, then I can have my pullbacks, but the system still compute. I don't have to solve relations in order to figure out the vector field of my system. Okay, so the whole point of this was to get the right notion of morphism. And that's what we have here. So what is a morphism of stateful lenses? Well, the setup here is, well, okay, so before we can ask what a morphism of stateful lenses is, we actually need to just know what a morphism of arenas is. Because a morphism of stateful lenses is going to fill in a square that looks like this. So A bar A, 1, 1. What? Yeah, it's a dependent set, but it could be anything, like any doctrine. But notice now that the doctrine actually needs pullbacks. Yeah. So A2, update, B2 bar. Okay. So the stateful lens morphism is going to fill in this diagram, and we're going to call this one S1 phi. Phi is like basically R and F combined, and then phi1 S2 phi2. And these are charts. So basically a chart is a function from A1 to A2, and then a function from A1 bar to A2. So like a lens is like forward back, a chart is like forward forward. And so a morphism alpha, basically the only data of the morphism is like alpha goes from A in A times S of A to S1 of A1 and A1 to S2 of I'm going to call this G H of G A1. And in the fibered perspective, if we're thinking of these like this, then it's something like A1 X B1 X1 A2 2 2. So it's just a span morphism. And so in the indexed version, this is sort of, this square is implied by the type signature, and this square is the first condition, which is the readout. So if I'm in a state and I read out a B from up here, and then use H to move from B1 to B2, then that should be the same as going from a state here to a state here, and then taking the readout. The second condition is the feedback condition. So this feedback condition says that if I get an input here, and then use this state to map it back, and then map it down here, that should be the same as mapping it down, then from the state here, deriving a state here, and using this state to map it back. And then finally, we have the update condition, which says that if I have an input here and a state here, and a new A1 here, then updating the state here and then mapping it down to a new state here via alpha should be the same as mapping the update down, mapping the event down, and then updating this. And so this is really great because this notion of two-cell gives us a property gives sort of a property of this double category that our old definitions didn't, which is that now trajectories of stateful lenses are representable. So what does this mean? Well, intuitively, like a trajectory is saying, like, okay, I start in a state with an A1 and a B. I start in a state with like A and B, and then S, and then I have like a sequence of inputs here, and the sequence of like new states here, and I just like chug it along. And that is represented by a map out of this stateful lens here. Bar A, B bar. So these charts on both sides, they pick out a sequence of A's and a sequence of A bars, and a sequence of B's and a sequence of B bars. And then, so this update, there's no state here. But the fact that this state space depends on this means that this arrow actually also depends on here. So instead of just getting one state here, I actually get a sequence of states, one for each time. And then the feedback and update conditions basically say that whatever I got, like the event that I got here was given by the feedback rule for here, and the next state that I got here was given by the update. So all of the readout, feedback, and update conditions are precisely what you want for defining a trajectory of this. Yeah. So and this is like something that is one of the big selling points of DCST, that trajectories are representable. But in DCST, trajectories were representable in the sense of like a double operad, which was fairly complicated. Now trajectories are just representable via normal two cells in just a double category. And then, so I really don't have time to go into this at all, but the double category of stateful lenses is Cartesian. So we know messing around with symmetric monoidal stuff. Once we've defined this double category, it's just the way that independent composition works is just a property of the double category. It doesn't come from any additional structure. Okay, so now we're on to 6. We're 5 minutes behind. Basically, all I'm going to say about here is that, so any lenses inject into stateful lenses, and more machines also inject into stateful lenses. So the traditional directed wiring diagram picture, where this is like some directed wiring diagram and these are all more machines, that just works, right? This is a morphism from 1 to like A bar A, and then this is maybe like D bar D, B, C. So I like more machine, more machine, more machine, directed wiring diagram, compose them, I get a new more machine on D bar D. It turns out, and I don't have time to go into this, that resource sharers are actually the exact opposite, which is that I can interpret an undirected wiring diagram as a stateful lens that looks like this. And then a resource sharer turns out to be a stateful, so it turns out to be a morphism out, like a morphism into the terminal object. And basically, like, this lets me put like a resource share on each of the inputs to UWD and get a resource share out by just like flipping around the direction of the operand in a sense. It's a little weird. And the intuition here is that each of these resource shares, they pass, remember the output in this direction is like an event. And in the continuous time, like the output is like a direction. And basically, you can think of each of these resource shares is exposing their resource and saying, like, what direction do I want this resource to go into? Then the undirected wiring diagram is like aggregating all of the ways in which the resource shares want to act on the resources, and then deciding how the resource ends up going. And the interesting thing here is that this actually points to a generalization of resource shares. Typically, resource shares, they just add up all of the vector fields from their components. But now the diagram actually here has the flexibility to choose how it aggregates, how each of the resource shares want to act on their resources. For instance, it could take the average. It could do something that depended on the state of some other component. It could have, like, you know, a Moore machine here that was telling it how to aggregate the demands on resources. So I think that's pretty interesting. Okay. Yeah. So that's all I'm going to say there because I'm about out of time. So in the last minute, I'm going to talk about future work. So part one of the future work is to write all this down and implement it, because this is still very much work in progress. But part two of future work is that whenever I think about dynamical systems, I don't want the state space of a dynamical system to be a set. I want the state space of a dynamical system to be a category, because I don't just care about where, like at time step 1 you're here, at time step 2 you're here. I care about, like, what was the process that moved you from time step 1 to time step 2. For instance, if I think of if I have a state system where the states are natural numbers, and I want to think of those natural numbers as giving me the length of a list, then I don't just care how the length changed. I care about the actual list operations that caused that length to change. What elements were deleted? What elements were added? Where were they put? And so that's more data than just like, oh, the list length was 6 now the list length is 7. So and in order to account for that within stateful lenses, I want to move from like the manifold being the base space here, or a set being the base space here, to a category being the base space here, and then the bundle given by a Condorcet vibration, also known as a pseudo functor into prof. And then the last thing, as a bonus, before I decided to go with notebooks, with cards and this and whiteboard, I wanted to like program, I wanted to like write a little program for slides. And I realized that actually the design pattern for the program that I wanted was exactly a stateful lens. Namely, it would be a stateful lens from this would be slide name, and then the events would be slide name plus next or prev. So the idea is that like the state here should be compatible with a certain slide number, and then it should output DOM to actually render, and then given a DOM event, it should either jump to another slide number or go to next prev. And the interesting thing here is that there's not necessarily an order that something over here is actually interpreting the next and previous. So this machine doesn't have to know the order of the slides that it's in. It just can jump to another slide by name, or it can say, I want to go to the next or previous slide. And the reason for that is that I don't, when I add extra slides, I don't want to have to like refactor where I'm jumping to with the next and previous buttons. Anyway, so that was just sort of a fun side note. Okay. Yeah, I made it. Yes, Dana.
You spend a lot of time on composition here, but of course, quite different machines may be doing the same thing. How do we compare different machines that aren't related by composition, but what do they do? What do they actually accomplish?
Yeah, so the idea is that these vertical morphisms, these two cells in the double category, are relating to different stateful lenses. And that allows you to say, like, okay, maybe this is a very complicated stateful lens, but when it's in a very particular regime of state space, it has some simple behavior. Then if this is a stateful lens that just like implements that simple behavior in a certain regime, then this morphism can witness that as long as we like stay in this regime, this stateful lens can be simulated by that stateful lens. I don't know if that makes sense. Yeah.
I'm wondering how the story connects to what you said in the very first pane here, where you have these two different views. Where one is like the kind of like classic algebra, like ideal view, and the other is like the piece in the view. Is what you're saying? Does the first of those have anything to do with this, or?
Yeah. So, the reason I sort of brought that up is because like stateful lenses allow you to sneak some of that gluing back into the lens framework, because the state is a span and these composed by pullbacks. So it allows you to get a little bit of that undirected feel, and also like, you know, in undirected wiring diagrams and resource shares, they also have a similar feel because they compose by setting parts of themselves equal. So you can recover a little bit, not the full generality of like, oh, I'm just going to put arbitrary laws in my system and then go to town. We're not going full MTK here, but we still get a little bit of that like gluing together vibe via the fact that composition is given by spans. Yeah, Kevin.
Just trying to understand some of your last examples a little better. So the more machine in page 6 is
This.
stateless, right? Because that's just
No. This has a state.
Wait, the state. Oh yeah.
The state is.
You used to think. What? Yeah. Will you? I kind of followed that, but will you just finish that sentence?
Yeah. So the state is like the, you know, there's a span here from 1 to A, and the state is the apex of that span. Oh, yeah. I guess I didn't mention that very explicitly, but the tangent bundle is, yeah, I think I've erased it now, but the tangent bundle is in this update. So the fact that this update takes in an A prime and produces a new state. So this is the discrete version where the tangent bundle is just, what new state am I doing? In the continuous case, I would actually this would actually be a vector, a tangent vector here. So I would have like, yeah. Well, actually, so in the continuous case, this would be, instead of a new A1, this would be a tangent vector at my first A1, And this would be a tangent vector at my S.
So is the S in that continuous case the entire arena STS?
Yeah, let me actually just write it out. So the update looks like TSS TA A times B bar the update looks like that. So like, yeah, given a state, you know, I have, it's compatible with input and output. And then given a input on my B and a tangent on my A, I get a tangent on my S. Cool.
Is this a preliminary thesis outline?
Sadly, no. It could be someone's preliminary thesis outline, but yeah. But I hope that I'm so, you know, part of the ARIA grant that we just got is David Jazz is sort of going back through double categorical systems, his double categorical systems theory, and sort of trying to clean it up and make it more more user-friendly, and also maybe write some like actual papers on it rather than just having a PDF that he hosts on his website. And so I'm hoping that sort of taking that shifting from this like 6 different things and a structure of monoidal composition to just 4 different things, the components of a double category, and the property of being Cartesian. I think that can simplify and unify a lot of the classical double categorical systems theory, and and so while we're like working on double categorical systems theory over the fall, we can start moving in that direction.
Okay, better thank Owen one last time.